Doppler effect, which is how we get redshift and blue shift when we're looking at stars and other objects that are significantly far away. When we are talking about those individual properties, we want to make sure that we've covered a little bit more in detail. So we're going to start on reflection. What things have you guys already discussed, do we already know about reflection of any wave? Okay, so we can talk about, for a continuous wave that reflects on itself, we can get a standing wave, absolutely. What else can we talk about in terms of reflection? Okay, so whatever it goes to, it comes back, so we have to have the same amount coming back. Pending no dampening, okay? Okay, so you're starting to get into the law of reflection, actually. So I'm just going to indicate that reflection is the bouncing of a wave off of a different medium. So when a boundary between two mediums is reached, a wave can bounce off of one and back into the original. So when a wave meets a boundary between two mediums, it bounces back into the original medium. And it does so according to the law of reflection. Law of reflection. So Brennan had just indicated that when a light wave strikes a surface, so this is going to be my surface here, this is just a normal to that surface. And I've got, where is my orange marker? I swear, all my stuff disappears. And we've got a light ray that's inbound, and it strikes a surface. It's going to create an incident angle here. I'm going to call this theta I. And then it bounces out in this direction. And we're going to call this theta R for incident and reflected. Now, this is probably the most intricate math equation that we've talked about yet this year. So I might have to go over it a couple times. Let me know if you've got questions on it. Mathematically representing the law of reflection, theta I is equal to theta R. So the incident angle is always equal to the reflected angle. Like I said,
give myself some room to write out a very long
possibly the most complex one that we've encountered. And this was discovered by Newton, so we've got a while back that we're talking about here. So, incident angle is equal to the reflected angle. Like actually? Okay. So, talking about this, if I just take a mirror, you're seeing directly back up into the camera, right? Okay, so I'm going to instead take my pen and place it here. So just looking at the pen through the image of the camera or the reflected image off the mirror, you see the top or the bottom of the pen, right? Well, if I want to see the pen cap, I can angle the mirror, and now my normal for the mirror is pointing at 45 degrees. So I can indicate the incoming light ray going this direction, and what do you now see? Top of the pen. So that means that the incoming light ray must bounce off of the mirror at that 45 degree angle and come up. In a dark room with more like dust particles in the air, we could do this with lasers and set a whole bunch of normals to those mirrors, and we'd actually be able to see this very easily. I believe Newton did it with candles and focused light. Okay. Questions about the law of reflection? So I'm doing this using a flat mirror, and flat mirrors are really the one that we're very used to. And anytime we're using a flat mirrors create what we call a virtual image. So this is my mirror surface, like that. As you look into a flat mirror, light rays are coming from specific locations on you, bouncing off the mirror, and traveling to your eyes. Obviously still forming that law of reflection with the normal from the mirror. We could also take a look at the light coming directly from your face, which then backtracks onto to you. Now, the apparent path of that light comes from the other side of the mirror. And the apparent path comes from an equal distance on the opposite side of the mirror at the location we call the virtual image. So, creates a virtual image. Have you guys walked by the mirror upstairs by the English hall, the English and Social Studies team centers, and had it look like it's clean enough that it looks like it's actually just more hallway, and that through the mirror? Do you get what I'm talking about? Or you've looked at a mirror maybe in a fun house or something, and it seems like that should be continued hallway, and like you should be able to just walk through it, but no, there's a wall there. Yeah. That's what we're talking about when we're talking about a virtual image. It appears to your eyes as though it actually exists. Your attention's back up here. So the human eye has no way of distinguishing between a virtual image and what you're really observing, so long as the mirror is good enough and you're not recognizing that in your brain already that you know there's a mirror there. We have to have other cues in order to recognize that the path of light is actually being obscured or is not the real path of light. Does that make sense? So a virtual image is the apparent path of light and our eyes, or our brains really, need additional cues to separate that from a regular image or from this or source of light. It is largely, yeah. Because by taking out everything else, you're removing all those other cues that our brain needs to recognize this as something else or not the original source of the image. As virtual. Okay. So along those lines, and just talking about VR, anybody read the book Ready Player One? Yeah, that movie's coming out next month. Yeah, I'm ready for that.
What if it's terrible?
It will not be. Do not speak such things.
Some people said it was Batman versus Superman.
No, they didn't.
No, people said it was supposed to be.
So in addition to flat mirrors, we also use two different types of mirrors, guys. We also use two different types of mirrors and the ideas from the law of reflection in order to manipulate light rays to our benefit. So the first one we're going to look at are convex mirrors. A convex mirror is a mirror that's bowed out, and it's designed so that light rays that are incoming get spread out into new directions. Alternatively, if we take light from multiple sources out here, they all get redirected. A little bit of that light gets redirected into a single location. So, let's say a convex mirror here. Okay, where have you seen these?
Up in the corner.
Like at a turn.
end of a hallway, especially in hospitals.
Or like restaurants.
Restaurants.
When I was in Boston, I had a bunch of
Corners of streets. I'm also thinking like corner shops, stop and goes, so they gas stations can see what you're doing. So general purpose of these mirrors is sort of safety and security, right? Because safety, so you've got a larger field of view, you don't crash into people. We should probably put one above my door so you guys can see around the corner here in this hallway. In addition to that, security, so people can see what's going on in your store or that kind of situation to avoid shoplifting. Looking at yourselves in the mirror here, what do you notice? Give me details. Larger field of view. Looks like you're far away. Anything else?
Looks almost like we're looking into a classroom with another.
Okay. So almost like you're looking into the classroom through like a wide-angle lens, almost. Okay, sure. I kind of think I should mount this here for my freshmen, so if I'm writing on the board, I can see what they're doing. So when we talk about it being for safety and security, a convex mirror gives you a wide field of view, but lessens the amount of detail that you're able to see. So widens field of view, decreases detail. For those of you interested in it, light is more an AP2 topic. So in terms of mirrors, this is really about as far into it as we go, is to recognize what the law of reflection is and that light is a wave. The last piece for reflection that we've got then is the concave mirror. Write that one down. Concave mirror. A concave mirror does the exact opposite thing. So light comes in, bounces off a point. Again, the normal for each of these different locations on the mirror is different from the other ones. And this causes all the light to actually bounce through a single location. That location is called the focus. A concave mirror is different from a flat mirror in that a concave mirror can then create what we call a real image. So to do that, first of all, a few things here. Concave mirror. You're upside down. Okay, that was the first option. So it looks like a lot of you guys super blurry, but very close up. Okay. If I get it just the right way, I can get a lot more detail here. And I can zoom in if I get it just right. They're kind of blurred.
That's what they use for.
Yes. So concave mirror, a lot less field of view, very narrow field of view, but this is used to show greater detail. This is what's used in all telescopes, satellite dishes. You've all seen those TV shows where they have the listening devices and they're trying to eavesdrop like across the street. Same exact idea. They're using some kind of concave mirror to reflect all of the sound waves to a listening device.
Oh yeah.
Yep, that's the exact same idea. Okay. So what we're talking about then is focusing of a large area of waves into a small area. What animals have the best eyesight?
Eagles.
Eagles are pretty good.
That's actually subjective. What do you mean?
Eyesight, best eyesight. Like if you zoom in the best and get the most detail. Owls. Owls are among the best eyesight in the natural world. Why do owls have the best eyesight? Hey guys, pay attention back up here. Owls are amongst the best eyesight in the natural world because they have the largest eyes. When we talk about telescopes, we use the same idea. Surface area is the most important thing we're talking about collecting area for a telescope, for a satellite, for a listening device, because the more waves you can collect from a larger area onto a single location, the more detail you can get out of those waves.
When you talk largest eyes, is it like comparative to the size of the body as well?
No, it should not be comparative. So you would think certain large fish would have better eyesight.
Or like an elephant?
But I do believe other evolutionary factors are important with those because, okay, the fish, they start to lose out on it because water sucks to see through.
Yeah.
I don't know why elephants wouldn't have better.
Could you assume their eyes are
I would think that they're pretty big, but my understanding is that they've got other evolutionary factors that cause eyesight to not be as important. Whereas owls have the advantage of large eyes, and it's really necessary for that. So, all right. Last one. Say it again. Large ears. We can talk about large ears. So, last thing on the telescopes concept. Any of you guys seen GoldenEye, James Bond movie?
Yes.
Okay, so way more than I had in the last time I asked that question. Yeah. For those of you who have seen the movie GoldenEye, for those of you who haven't, you should probably watch it. It's a James Bond classic. But the last set of combat scenes that they've got, where they're up in that like catwalk of that giant dish thing, that is actually a giant radio telescope that they are just shooting the scene on. That is a telescope in Arecibo, Puerto Rico, and it is used to literally scan the sky for radio waves that we're using to map different things, other galaxies, other stars. They also use it for a short time being for SETI. That was a flop. But it's a very large telescope that has a diameter of, I believe, like 100 meters. So again, when it comes to surface area for these, bigger is strictly better. Okay, so used for satellite dishes, telescopes. There's the other one, the compact mirror or the shaving mirror, any of those kind of things. Okay. Any of those kind of things would use a concave mirror. All right. Talking about reflection, I also then have to talk about complete internal reflection. Complete internal reflection is something that occurs when the speed of a wave between two mediums is significantly different enough that a wave must strike the barrier between the two mediums at a steep enough angle in order to exit into the new medium. So, as a wave meets the barrier between two mediums, if the wave speed difference in wave speed between the two mediums is significant enough, if the difference between the two mediums is significant enough, The wave must strike the new medium at a steep angle in order to pass into it. Medium at a steep angle to pass into it. Alright, so this is the concept that we use for fiber optics. Fiber optics use complete internal reflection in order to basically just continually bounce off the edges of the same medium, because the difference in speed of the wave is too significantly different between the fiber optic cable and the air for the wave to pass from one to the next. So I'm using a green laser. You can see the point on the back. Roughly 200 milliwatts. Definitely enough to burn out your eye. So, side note, I had a professor who used to talk like this and use a green laser pointer over here. And then, without taking her finger off the button, she'd come over here and keep talking. And yeah, it was like playing Russian roulette with a laser pointer.
Did you see like a wave of speech?
Oh, you would. And they'd be like veering around and ducking down. It was absurd. So, taking the laser pointer, shining it into the fiber optic cable, getting this just right. First question, do you see any light on the wall over there? No. None of it's passing straight through the cable. You're also not seeing any light in the cable itself, right? Except for that point. So what you're observing is that the light is undergoing complete internal reflection, meaning it's bouncing off the edges repeatedly on the fiber optic cable, and the difference between the speed of the wave outside the cable and inside the cable is significant enough that the light wave has to hit the cable at a very steep angle in order to pass through it. So if I take it sideways, here's a steep enough angle, I'm going to pass straight through. Okay? I cannot get this to happen if I'm coming in at too shallow of an angle. Okay? Using a different medium, I can demonstrate that again. Here's why the fish tank's here.
Is that the type of laser that you would like get in big trouble for shooting?
Probably. All right, so what I want you to look at is as the wave, and let's see what we do here. Stir it up, see if I can get a little bit of dust in there. Can you guys see the beam of light at all? No. A little bit? Let me turn off the other light. Breeze?
Shit, shut that.
Okay. Alright, so there we go. So as it's going, what I'm looking for right now is, if I haven't made all sorts of waves, you can see it bouncing off the bottom of the fish tank, right? What I'm also looking for is, if I've got this at too shallow of an angle, I can also see it bouncing off the top of the water. So I just read spot. Can you guys see it bouncing off the top of the water? I had it a minute ago. Yeah.
Wait, so why is it?
Because the difference in speed of light between the water and the air is too great. And as that difference intensifies, I have to have the light strike at a more vertical angle in order to pass back out of that. So like up here, you can see the dot on the ceiling. Actually, you can see two dots on the ceiling, which we're going to talk about in just a second. And as I decrease this, there's a good one. So you should be able to see the laser bouncing off the bottom of the fish tank, and then, where'd it go? I had it. There it is. And then bouncing off the top of the water as well. You see it? So the second thing that we're looking at there is our next topic, which is refraction. As light passes from one medium into a new medium that has a different wave speed, light bends. This is also really what causes that complete internal reflection. Light here. Refraction. Let's use this one. Refraction is the bending of a light wave due to a difference in the wave speed between two mediums. Bending of a, and I shouldn't say light wave, I should just say wave, due to the difference in wave speeds between two mediums. Okay, so this one's this. What we're looking at then is as I've got a beam of light, so this is like 1 milliwatt, this is super weak, passing into the water, and I'll turn it so you guys can see too. Initially it's coming in at about 40 degrees, right? What is it then exiting at? Clearly not. What is it exiting at? 30, maybe 29, something about that. Okay? So as the light's going into the water, the light ray is then bending because it's entering a new medium with a different speed of light, or a different wave speed. Okay? So we can then actually use that information and something called Snell's law to figure out exactly what the speed of light, or the wave speed for light, is in the medium of water. And Snell's law is sine theta 1 divided by sine theta 2 equals B1 over V2. Had to make sure I'm getting the ratio right. Which is the same as saying N2 over N1. Now note, I did swap the 2 and the 1 on this spot. Where N is what we call an index of refraction. Index of refraction. And is found as N is equal to, I better look that one up, I'm going to screw that up. All right, where c is the speed of light in a vacuum. Okay. So looking at our setup that we've got here, speed of light in a vacuum is 3 times 10 to the 8th meters per second, roughly. So that means that if we look at our angles here, theta 1, sine of theta 1 is, well, that's 40 degrees. Divided by sine theta 2, well, that's probably about 29 degrees. And the speed of light in air is just below 3. So if I remember correctly, we're looking at 2.98 times 10 to the 8th meters per second, divided by V2. And we can then find what the speed of light in water is just based on algebra. Solving for this, sine of 40 divided by the sine of 29, and then 2.98 times 10 to the 8th divided by, oops, that's not what I wanted to hit, crud. 2.98 times 10 to the 8th divided by that value gets me an answer of 2.25 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 meters per second, showing a significantly slower wave speed in water. All right, good so far? Now, we can actually predict at what angle would these start to break down, and would these start to not reflect, or refract rather, based on simply looking at the sine functions. So if we wanted to find at what angle would light no longer bounce out of the water, and would it only be able to reflect, and we'd start to see complete internal reflection, all we've got to do is make this an impossible equation to solve. Meaning that if either of these angles caused the sine value to say, if this became sine of 0, then my equation would no longer function correctly, because I can't divide by 0, right? Okay. If my sine value, so if sine theta, and it can be either one, needs to be less than 0, less than -1, trying to get my math signs right, and greater than 1, did I put that backwards? So it needs to fall, the value for sine theta needs to be between -1 and 1. So I need to face the other way? It's good? So sine theta and then 1. So it needs to be between those two values. And it can be equal to. If it is 0, then this value will also be 0. Because you can multiply them up to the other sides. Yeah. So sine theta in all cases must be between -1 and 1. If it is not, we observe complete internal reflection.
If it was 0, would that mean any angle you shine at
No, that would mean at 0 degrees, it'd be straight down. And it comes straight back up. Because you measure the angle from the normal. Yeah. So like that would be like 15 degrees, 45 degrees, 90 degrees. Complete internal reflection occurs. Yes, I did use the right word there. All right. Now, tools where we can talk about refraction. Obviously, this is a pretty easy one to think about in terms of water. Yeah. If sine of theta needs, or if's a bad term there. Does that fix it? Okay. Sine theta needs to be between -1 and 1. If it is not, complete internal reflection occurs. Does that make more sense? Okay, thanks for calling me out on that. All right. So, two situations where we're going to talk about these. Obviously, we can talk about it in terms of water and air. Anybody ever been bow fishing or spear fishing? Okay. Where do you have to aim to hit the fish? Right, you've got to aim below where the fish actually looks. Because if you try to aim right at the fish, well, we just demonstrated that the light's not coming from where it appears to be. So the fish is actually not where it looks like it is. It's actually below where it appears to be. So if you don't aim low by, as we just demonstrated, like 10 degrees, you're going to miss because the fish isn't there. Make sense? Okay. All right. So situations where we actually use this in a more common sense would be lenses. We have converging and diverging lenses. Let me see if I've got a couple examples. I got one of each here. So a converging lens is a lens where we can take this, and I'm just going to pick a letter here. And And what are you noticing is happening? It's magnifying it, right? Converging lenses are magnifying glasses in the most simple sense. What they're doing is they're taking the light over a larger area and they're focusing it onto one point. Same idea, and actually this is really the idea that eyes use. The bigger your eyes are, the larger the collecting area, the more information they can gather. Collects light over a large area and redirects it to a single point. So if I'm drawing this one out, here's my converging lens. You'll notice it bows out on each side. As light comes into the lens, it refracts and then refracts again, refracts and then refracts again, and crosses through a single point again called the focus. So this is magnifying glasses, refracting telescopes, which suck. We can also talk about many eyeglasses. Did I say microscopes? Okay. Yeah, those are our big ones. Oh, camera lenses. Camera lenses. Microscopes. Telescopes. Okay. The converging lens is also capable of recreating a real image, which is why they work for telescopes and cameras, because they take the image that's being observed and they redirect that light to recreate it at a specific location. Of creating real images. Okay. So if I were to draw a person here, and you're staring at a person through some large converging lens, we could then recreate that person depending on where your focus is at a specific location. However, you'll notice what happened to those light rays. They flipped, therefore they're upside down, which is why if it's held at just the right spot, the light ray is coming from, oh, this is a very long focal length. See if I've got a shorter one. Okay, so, oh, that one's upside down, showing that the light rays are in fact flipped. Now if I get close enough, I get to the other side of the focus. They're up, right side up. As I pass through the focus, they flip upside down. So you can see the word needs, yes. It's upside down, I'm on the other side of the focus. I pass through the focus, and you see needs, and it's right side up. All right, the other kind of lens that we see are diverging lenses. A diverging lens takes incoming light and spreads it out. Oh, that was a terrible drawing. Again, using refraction. Yes. So taking a look at the word lenses here, what are you noticing here? Okay, it's incredibly small, right? So that's because the light is being spread out. So any light that would have been absorbed or directed at your eye is now directed at multiple locations, so you get fewer and fewer incoming waves that actually strike your eye. Okay. These guys can be used as the eyepiece on certain telescopes, basically to avoid having the image flip if they're placed at the right spot. But more practically, certain prescriptions of eyeglasses. Depends on what your prescription is. I don't 100% know how it works because that's going into the realm of biology. But depending on what your eyes need to have fixed, you may have a converging lens, you may have a diverging lens, trying to account for what bend the light actually needs, whether it needs to spread out further or focus in closer. That is my understanding, yes. All right, questions on converging or diverging lenses? Okay. Then the last topic that we get is diffraction. Diffraction is the bending of a wave as it reaches a corner or an edge. Bending of a wave as it reaches an edge. This is why, if you're standing in the hallway, you could probably hear me talking. In addition to echoes, sound waves bend as they go around corners. We could also see this if you were, say, in a pool, and you were sitting right here splashing. Sure, you're going to have waves propagating out directly from you, like this. But then when they reach this corner, they don't just continue and this is all you get for the waves. That'd be absurd. You start to see waves over in this region as well, right? So you see waves that start to curve in through here. They may be weaker in amplitude, but they do travel out in this direction. There's usually a small silent spot where there aren't as many waves, or any waves in many cases, but these ones through here will propagate as they bend around the corner. We can also demonstrate this with a light using a piece of paper. All right, so I'm going to kill the lights real quick. And we've got a green point on the back wall, yes? Nice, moving, relatively solid dot. Let's see if I can get that a little steadier. That's a little better. I'm going to take a piece of paper and I'm just going to slide it down until the light and the paper are basically at the same location. I want you to watch what the light does. Let me get it there. What are you noticing the dots doing? Say again? Getting smaller. What else? Okay, reducing the outside part. Not as bright. Oh, I can't get it to work right now. Let's see if I can do it over here. A little bit. This is a darker spot. Okay, so you've got the dot here. So that's a nice, well-defined dot here, yes? What's happening to the dot as I'm bringing the paper down, other than it's getting dim? What's happening to its concentration?
It's more concentrated in the center, and there's less around the edges.
Okay. So, wow, I am really botching this. I did it really well yesterday for the regular physics class. There we go. What happened to the dot? Spreads out. You get that line, right? So what's happening there is the light wave is bending around the piece of paper, and it's bending around in a perpendicular fashion. So if I've got the paper lined up this way, then the light beam bends out in this direction. If I've got the paper this way, the light beam bends out in this direction. No, that's a different concept entirely, which we didn't have time to talk about today. Yeah, we're going to. But we'll have to do it tomorrow because